Bismillahirrahmanirrahim. In this video, I'll try to clarify some of the confusions related to complex power. And primarily, one of my students has asked this question, that why we need conjugate in a complex power calculation, and when do we use KVA or KVAR for the reactive power. So let's see. We have learned that the impedance triangle is a triangle like this, which represents the resistance and the reactance and the impedance like this. So this is called impedance triangle. Exactly same way we use a power triangle to represent the three types of power. This one is the real power P, then reactive power Q, and this is the complex power or also apparent power. So the power triangle is used for studying power. Now, if the load is inductive, then we draw it like this. The reactive curve goes up, and this is the shape. But if it is capacitive, then it reverses, so it goes down. So this is for the capacitive load. But since in the industry primarily we have inductive loads, and therefore we'll primarily study or use this diagram for inductive load. Okay, so first thing is the active power. What is active power? The power used or consumed by the load, that is actually the resistive load consumes power only. So this is the active power or actual power used by the load, and it is measured in units of watt. So whatever our energy meter reads, that actually is the power consumed by the resistive elements, and so that is why its unit is watt or kilowatt, etc. And there are several names used to confuse us. One is the real power, then it is called actual power, it is also called true power, it is also called wattful power, and it is also called useful power. So keep these things in mind. Now, if it was a DC circuit, we know the power is V into I. But for AC circuit, we need to modify the formula. It will be VI cos theta V minus theta I. So this angle is theta V minus theta I. And actually, if you look in this diagram, so this is the real axis. The voltage phasor makes an angle theta V with this. So this angle is theta V. And the current phasor makes an angle which is called theta I. And in between the two, we have theta V minus theta I, that is theta V minus theta I is the angle between voltage and current. So that is why we have written here theta V. Okay, next we come to the reactive power. Now, to understand this, if you just assume that we have an inductive load, so what happens into the circuit? When the voltage is rising up to this point, it is charging the inductor. So the current is flowing from source to inductor. The moment it starts reducing from the peak, then the inductor will start charging the source or start giving the current back into the source. Similarly, when it comes here, again the inductor will start charging. So it will now flow like this, and the moment it goes or crosses the third quadrant, then the current will start flowing back. So we call that the current bounces back and forth between the source and the load. Now, if you have an energy meter or power meter that we connect, it will not be able to read any power because this is happening very fast, and so you will not get any power reading, and you will not get a bill actually for this. We'll study that in the next video. So this is this power is called the reactive power, and we represent it by Q is equal to Vi sine theta V minus theta I. So this power is, we use sine. As you know that for the perpendicular the formula is for sine, and for the base the formula is cos. So same technique here. So we are using Vi sine theta V minus theta I. Now the question is, what should be its unit? Okay, now let's compare it with the active power that we have calculated, this one, and its unit we said that its unit is watt. Now if you compare the two, we have Vi and Vi, then we have sine, and here we have cos. Now cos of some theta is a number. Similarly, sine of some theta is also a number. So basically their unit should be same. V into I, and multiplied by some number. So technically this should also be called watt. But then how do we distinguish whether this is part of the active power or it is part of the reactive power? And I give an example of two of my friends. They were both called Javed, but one was short-heighted, and therefore we used to call him Javed Shorty. So this is to distinguish between the two. Exactly same way, to distinguish between the two, instead of calling it watt reactive or watt something, we just call it VAR. So its unit is VAR, or volt ampere reactive. Okay, and now we come to the complex power. Complex power is the summation of the two. This plus this, whatever we get is the complex power. So we can call it that the complex sum of real power plus reactive power is the complex power. So S is equal to P plus JQ. This plus JQ. And as we discussed, there are several ways of writing this. All these we can use to calculate the complex power. Now, a term, apparent power, becomes very confusing sometimes. What is apparent power? So, apparent power is the magnitude of the complex power. So, if this is complex power S, then its magnitude is the complex power with the phase angle ignored. And to make it easy for you to remember, I have used this picture. You see, this guy with uniform or with phase angle, we can say, is the complex power. And when you delete the phase angle, like this was the formula for complex power, Vrms, Irms. If we ignore the angle or delete the angle or remove the uniform, so whatever is left is apparent power. So the apparent power is only the magnitude, not the angle. So magnitude of complex power, and so it will be written as Vrms, Irms. And so from here, P and Q, and on the same triangle, it is complex power, and it is also apparent power, that is the magnitude. Now, some people have confusion about KVA, KVAR and KW. Let's again take help of the diagram. You see, the real power, we learned that its unit is W. The reactive power, we have named its unit to be VAR. And so the apparent power or the complex power is simply called VA, that is volt multiplied by current. And when the units get bigger, then we just write kilo with it. So this is kilowatt, this is kilo VAR, and this is kilo VAA. So if you look from the generator side, actually this is the supply source, this is supplying, and it is being used by the resistive element KW, and it is used by the reactive element KVAR. So that is why the generators, transformers, etc., they are rated in KVA, because this is, we can say that this is the supply end. Okay, same here, the power for reactive or power for reactive, and the VA or KVA is for the complex and apparent power. Okay, let's have an example to clarify the concept. The voltage is given by this formula and the current is given by here. If we plot it in the phasor form, you see this has an angle minus 10, so we draw it here on the negative side, minus 10, and the current has an angle of 50, so we draw it on the positive side. And now to find the complex power, we file first of all these are the two, and we can write it in or we can use any of these formulas to find the complex power. Let's say I want to use this formula, then for this I have to find Vrms and Irms. So from here I can first of all write it in phasor form. So V maximum or V phasor is the magnitude and the angle, minus 10, and here also it is 1.5 and the angle. And for RMS we divide by under root 2. So this is the RMS value. And now to use this formula, I'll just write this formula, and this one you see is we have taken conjugate. Here we have taken for plus 50, we have taken minus 50, the conjugate, and if you multiply these two, we will get 45, and add these two angles, we will get minus 60. So this is the complex power. And now apparent power, this guy, so remove the uniform or remove the angle, so whatever is left is the apparent power. So magnitude is 45 VA. Now what are the advantages of complex power? You can see if we know the complex power, all we need to do is use our calculator to convert it into from polar to rectangular. So we get this answer. So the first part is the real part. So this is our real power or true power, and it is in watts. And the second term is our reactive power. So this is in 38.97. This is in VAR. So instead of calculating the real power and then calculating the reactive power and then adding the two to get the complex power, if you go the other way around, it becomes so easy. First calculate the complex power, use your calculator, and you directly get the real power and reactive power. Okay, now the student has also asked why we use I conjugate. Well, one thing can be written in several ways, and if in this case, if I want to use this formula, I can simply use the formula, the magnitudes, values, and the angle minus 10, minus 50, and this way I can calculate the complex value. And now if I want to use the other one, there's no harm. I just give an example here. We used to solve the subtraction problem by this, that is 5 minus 3 is equal to 2. Now the new teaching says, no, you should actually write it like this, that is 5 plus minus 3 is equal to 2, and this you can easily get from the number line. So from 0, let's say this is the 0 point, you go 5 to the right, and then you come back 3 to the left, and wherever you are, that is the answer. So the one question or one thing can be done in 2, 3 multiple ways. Same here. What we are doing is, in the case of a I conjugate, we are just changing the angle of this one, and then we can directly use this formula. So we can directly use this formula or this formula. This is in the phasor form. Since we have the answer in phasor form, so we can use directly this formula. So we half V phasor 60 angle 10, 60 angle 10 multiply by I phasor 1.5, and now we adding here the plus angle minus 50. So plus angle minus 50, we get the same answer. So there is no harm whichever technique you use. I hope this gives you an understanding as to how to solve this type of a problem or clarify your confusions. If you still have any doubt, please write to me your questions. Thank you. Don't forget to share with your friends and subscribe the channel. Thanks.